Okay, now let's move to radioactivity subtopic. Alright, so if you refer to this diagram, this is photographic plate, okay, made by Henry Becquerel, showing effect of exposure to radioactivity. So actually, Becquerel accidentally discovered that uranyl potassium sulfide crystal emits an invisible radiation that can darken a photographic plate even though the plate is covered to exclude light. After a series of experiments, he concluded that the radiation emitted by the crystals was a new type, one that requires no external stimulation. It means that naturally, spontaneously decayed or emitted by the crystal and was so penetrating that it could darken protected photographic plates and ionize gases. This process, as I mentioned just now, is spontaneous emission or radiation by uranium was later on called as radioactivity. Subsequent experiments by other scientists showed that other substances were more powerfully radioactive. The most significant early investigation of this type were conducted by Marie and Pierre Curie, husband and wife. Okay, after several years of careful and laborious chemical separation process on tons of pitch blend a radioactive ore, the Curies reported the discovery of two previously unknown elements, both radioactive, named as polonium and radium. Okay. Additional experiments, including Rutherford's famous work on alpha particle scattering, suggested that radioactivity is the result of the decay or disintegration of unstable nuclei. Right. So, it is discovered that the radioactivity disintegration or the decay process by the radioactive material producing three types of radiation. First one is alpha. Alright, this is coming from helium atom. Right, so this is actually alpha here. Is actually originate coming from helium atom for 2. Okay, so it has electrical charge, it has mass. Okay, the biggest compared to the other two types of radiations, okay, in terms of mass and also charge, and it's positively charged. And second type is the beta. So beta here or also symbolized as electron or also known as negatron. Okay, is actually a kind of electron. It has two types, right? It has two types were commonly known as electron or negatron, and the other one is positron. Certain book it has symbol of beta negative like this, or positron is symbolized as this. So between these two, the amount of the charge is the same, which is one elementary amount of charge 1.6 times 10 to the power of negative 19 coulomb. However, the only difference between negatron or electron with the positron is actually the type of the charge. For this one, it's negatively charged. For this one, it's positively charged. Right? So, the third one is gamma. Okay, gamma has no electrical charge. Okay, no electrical charge. Okay, and has no mass. It's simply high energy or photon. Okay, and how to distinguish between these three types of radiation in terms of electrical charge of them, the mass, right, and also the ability to penetrate material. For example, for alpha, since it's quite big in mass and also charge, it only can penetrate a sheet of paper, and then it's going to be captured here because the energy already gone. For beta, okay, it can penetrate the paper here as well as, okay, few of aluminium. This is maximum. After few of aluminium, the energy will be all of it captured within this. Okay, so the beta won't have any energy left. Right. For gamma, it's even highest in terms of energy. It has no electrical charge. It has no mass. So the ability to penetrate is the highest among of all. Okay, it can penetrate several centimeters of plumbum. Right? So this is in terms of ability. We also can carry out some experiment by using magnetic field, where we are going to observe deflection of movement for alpha and beta because it has charge. But there is no deflection will be observed, okay, when placed within magnetic field for gamma, since it has no charge. We will discuss in detail about this within Physics 3 later on. The decay process is a probabilistic in nature and can be described with statistical calculation, right, for a radioactive substance or macroscopic size containing a large number of radioactive nuclei. So means that the rate of decay is directly proportional to the number of the nuclei that have not yet decayed. And this one is in negative because it's decreased in amount. When we want to convert it into mathematical expression, the rate of the decay is equivalent to negative, must be a constant at this side, isn't it? Lambda n. The constant here, we call it decay constant, right? So the decay constant tell us about the probability of the decay per nucleus per second, right? So that is how, okay, we have this equation. So from this equation, now we can rewrite this equation into this. Upon integration of this equation, we will get n equivalent to n naught E negative lambda t, where the n naught now represent the number of undecayed radioactive nuclei at t equivalent to 0. So the rate of the decay, okay, is symbolized as R, is equivalent to modulus of dn over dt. Why is it modulus? Okay, it's because rate, we only consider magnitude of it, which is going to be equivalent to lambda n. Our n itself is n naught E negative lambda t. So from here, we can say that lambda n naught here is actually R naught, the decay rate at t equivalent to 0. So this one is decay rate at t equivalent to 0. So what is the difference between this equation and this equation? Finally, we have R equivalent to R naught E negative lambda t, right? So what is the difference between this equation and this equation? This is talking about the number of the nuclei, okay? the number of the nuclei, right? Information of the number of the nuclei. And this is talking about the decay rate, the radioactivity of the nuclei. Okay, so this also known as decay rate or activity or radioactivity of the nuclei at T equivalent to T. So from this equation, as I mentioned just now, if we plot the graph of this function or equation, we will have this kind of pattern where it is a pattern of exponent. So for the time taken for the n, the number of the nuclei, okay, as a function of t, from the original number of it to become half of it, this is half of it, time taken or needed, okay, from n naught to be half of n naught is known as half-life, T half. So half-life means that the duration, the period needed for the nuclei to decay or disintegrate and become half of the original amount of it. Right? So from that, now our n is n naught over 2. Okay, which equivalent to n naught E negative lambda T half. So cancelling the n factor, right? So we will have T half is equivalent to ln 2 over lambda, which equivalent to 0.693 over lambda. So this is a formula to figure out half-life of a nuclei or the radioactive material. Okay, how about this one? So for the n here to become again half of it, okay, or in comparison to the n naught here is 2 times of the half of it or 1 over 4 of it, alright. So the time taken is 2 half-life. That is the meaning of this. 2 times of half-life, so that our n naught right now, n here right now, is equivalent to 1 over 4 of the original n naught at t equivalent to 0, and so on. Right, this is what I'm talking about just now. Okay. We can also have this pattern of equation. N equivalent to n naught times half of power n, where n can be integer or non-integer. So what is n? This is the number of the half-life. Okay, number of half-life. How many half-life? Right. And the unit for activity is the most common one is Curie, or also can be determined in terms of becquerel. So 1 becquerel is 1 decay per second. For 1 Curie is equivalent to 3.7 times 10 to the power of 10 decays per second. The one, the SI unit is actually this one. 1 becquerel equivalent to 1 decay per second. Example 43.4. The activity of carbon. At T equivalent to 0, a radioactive sample contains 3.5 microgram of pure carbon 11, which has a half-life of 20.4 minutes. A. Determine the number of N naught of nuclei in the sample at T equivalent to 0. So, given to us about 3.5 microgram, and we know this is carbon 11. First thing first, we need to know how many N. Okay, how many N, isn't it? Number of nuclei. So, from this information given, first thing first, we need to figure out number of mole. Alright, so given to us the mass, okay, carbon 11, okay, it's 11 gram per mole, molar mass, okay. So, it's equivalent to, number of mole equivalent to 3.18 times 10 to the power of negative 7 mole. Okay, from here, okay, N naught is equivalent to N times Avogadro number, because it tells us how many nuclei per mole. So you have 3.18 times 10 to the power of negative 7, the mole just now, times 6.02 times 10 to the power of 23 nuclei per mole. So the unit of the mole can be cancelled out. We are left with nuclei. That is the original number of nuclei undecayed at T equivalent to 0. B. What is the activity of the sample initially and after 8 hours? Initially, the activity or decay rate or radioactivity is equivalent to lambda N naught. Okay, and we know that lambda itself is equivalent to ln 2 over T half times N naught. So substitute the information and convert the T half into second, right? Then you will get your answer 1.09 times 10 to the power of 14 becquerel or decay per second or disintegration per second. Right? After 8 hours, the R, the decay rate or activity, is equivalent to R naught E negative lambda T. So, substitute the R naught that we calculated just now, and also the lambda, and also the T for 8 hours in second. You have to make sure the unit of this and the unit of this cancel out each other. Okay, because when you do exponential, supposedly this has no unit because exponential is mathematical treatment. So finally you will get 8.96 times 10 to the power of 6 becquerel or decay per second or disintegration per second. Example 43.5, a radioactive isotope of iodine. A sample of isotope iodine-131, which has half-life of 8.04 days, has an activity of 5 millicurie at the time of shipment. Upon receipt of the sample at a medical laboratory, the activity is 2.1 millicurie reduced. How much time has elapsed between the two measurements? Right, so we want to know the T. So originally we have R equivalent to R naught E negative lambda T. So make a ratio of it because our interest is the T. And then after that, ln both sides to eliminate the exponent. You will get this pattern. And finally, make the T as our interest. So you will get this pattern. And 1 over lambda is actually T half over ln 2. Because, okay, T half is ln 2 over lambda. Right. So to have 1 over lambda is equivalent to T half over ln 2. Then after that, substitute the rest of the information, you will get this answer. Right? 10 days of shipment. Okay, this is actually what happened to Malaysia. Okay, where all the radioactive material that we need to use for medical treatment actually are shipped from other country